So chapter 9, this is really about sampling distributions. I'm going to talk a little bit about that. So before we go too far into this, we really need to talk about some terminology. First thing is a parameter. And a parameter is a number that describes a population. That's probably why the P's are both red. Parameters do not change. The average height of, say, all the women in the United States does not change. And if it does, it doesn't change from one day to the next. Perhaps slowly over time it changes. But really it's a static number. And also, we don't know what the true height is, because the only way to really know what the true height is would be to measure every single woman in the United States, and that seems a bit unrealistic. A statistic. A statistic is a number that describes the sample. The statistic does change. So if we survey 5 people, let's say, their height could vary dramatically depending on what 5 people we sampled and the methods that we picked to sample them. And also, we always know what the statistic is because we can calculate it. Statistic sample. Okay. So the goal of statistics is to use a statistic to estimate the parameter. So what we would like to do is find a small group of people. From that small group of people, or items, we can then figure out some interesting tidbit about the parameter, about the population in general. For example, we would like to know what the average height of women is, based on, say, 1,000 or 2,000 women. So a sampling distribution basically says this. If we take several different samples of the same population, and we sample correctly, we can reduce the error in evaluating the parameter. Because the more times we sample, the more people we go back to pick, the better off we are. Now, just so you know, if we were sampling, say, everybody at Palmdale High, the same person could get chosen both samples if we were to say sample twice. Because after we sample everybody, we put their names back in, and then we randomly choose people again. Now, sampling distributions, like almost everything else, implies that we're using an SRS. So whenever we're saying sampling, what I'm really talking about is an SRS or some other scheme whereby I can sample people fairly. A little bit more about sampling distributions. We are going to look at the mean of means. So we're going to take a bunch of samples and find the average of that. And we're going to use this to approximate the parameter, hopefully with as little error as possible. And in fact, the best polls in the last presidential election use this mean of means idea, the average of the average. And when we graph a distribution, we want to look at it. And remember to use SOCS. And we'll talk a little bit more about this graphing in a moment. Give you a second to copy this, or to pause it rather. So let's talk a little bit more. So just some things so you know. P is a proportion, or a population proportion rather, or percent. It's going to be between 0 and 1. And that's a p hat. It's beautifully rendered. I'll try again. And p hat's our guess. Let's see if I can do a better job of it this time. P hat. That's beautiful. This hat here means guess. So anytime you see a hat, it's a guess of the population of proportion or percent. So it's our guess, our prediction, or our statistic. It's also our statistic. We somehow figured this out. Bias. Bias is how far the statistic is from the parameter. We call a statistic an unbiased estimator if it has the same mean or proportion as a population. So an unbiased estimator is a good guess. And a sampling distribution, again, allows for a reduction of bias. This idea that the more times we sample data, the better off we are, is going to be a reoccurring theme. We're almost done with this. So let's talk about sampling variability. If we repeatedly sample the same population, we will see a pattern emerge. It is oftentimes being the key word. It doesn't say always. It says oftentimes. The pattern is normal or uniform, and we'll discuss this more as the chapter progresses. And it says a sampling distribution is created by sampling a population, making a histogram from the means or proportions of these samples. N needs to be the same size in all samples. So if we sample 10 people the first time, we need to sample people the second time, third time, fourth time, fifth time, etc. Sampling distributions have a mean closer to the true mean of the population. And again, we don't know what the true mean is, so we're going to assume the more often we sample, the better off we are. And the variability, now remember, we define variability as standard deviation, is much smaller in a sampling distribution. And we will talk about just how much smaller, but not right now. So that concludes this, and wasn't too bad.